Throughout human history, we have worked together in a quest to interpret our world. The need to expand our knowledge gave rise to the fields of science, including chemistry, physics, biology, and earth science. We have learned about many individual fields of study in great depth for the past few hundred years. Only in the past several decades, however, have our technology, intellect, and passions combined to give us the ability to put many of the pieces of knowledge together. We are now developing a much larger picture about our Earth as a whole. It unveils a complex, interconnected, remarkable world, and it reveals the powerful influence we have had on our home planet. We begin perched high in Colorado's Rocky Mountains as the sun rises over Thwaites Ridge. In this isolated place, away from the direct influence of civilization, scientists are gathering data. They measure things like air temperature, wind speed, water runoff, the types of plants growing, when they flower, and the amount of snow. These scientists have been tracking how these measurements change for over half a century, and their data reveal a distinctive story about how our backyard is changing. Within these large canisters, scientists are separating and measuring the gases that make up the air. Almost all of the gas is nitrogen, oxygen, argon, and water vapor. Other trace gases have been carefully measured as well, like carbon dioxide, commonly called CO2. Why would scientists care about CO2, a gas that makes up less than half of 1% of our atmosphere? To understand why, we need to take a closer look at our atmosphere. On a sunny day, we can feel the warmth of our star, but how does the air react to this energy? All hot objects, the sun, the earth, even your own body, radiate light. The color we see, the wavelength of the light, depends on the temperature of the object. The sun is a scorching 10,000 degrees Fahrenheit, or 5,500 degrees Celsius, meaning that it produces mainly visible light, the colors of the rainbow. After traveling across the vacuum of space for 93 million miles, or 150 million kilometers, this light encounters the Earth. Some of it bounces off of the planet, reflecting off of clouds and ice, and we see these things as white. Light that does not get reflected is absorbed by the planet's surface, heating it up. After being absorbed, this heat does not disappear. The laws of physics reveal that energy cannot be destroyed. Some of that energy, the Earth re-radiates back towards space. At the Earth's surface, which is much cooler than the sun, this radiation is not a visible color. This invisible light can actually be felt as heat. Scientists call this radiation infrared because it has a wavelength that is longer than that of visible red light. Much of this infrared light does make it out directly into space, but some of it takes a detour along the way. The reason for the detour has to do with those certain very rare or trace molecules in Earth's atmosphere. Some molecules that are made of 3 or more atoms are extra sensitive to infrared light. When excited by the light, these molecules twist and vibrate. The same molecules don't get excited by light with shorter wavelengths, like the visible light from the sun. This is similar to how humans cannot hear the high-pitched or short wavelength sounds of a dog whistle, but we do get excited and even dance to the longer wavelength sounds of your favorite music. Infrared-sensitive molecules warm the Earth by slowing the escape of infrared light back into space. A variety of molecules in Earth's atmosphere can do this, but CO2, methane, and water vapor are all particularly sensitive to infrared light and causes a warming effect. Now, this warming is a good thing in moderation. Without any of these molecules in our atmosphere, Earth's average temperature would hover near 0 degrees Fahrenheit or minus 15 degrees Celsius. Instead, Earth is a comfortable average of 60 degrees Fahrenheit or 15 degrees Celsius. The higher the concentration of these molecules, the more the atmosphere traps heat before it escapes, further warming the Earth's surface. Scientists measure that the relatively tiny concentrations of these gases have big effects. CO2's concentration is a fraction of a percent of the whole atmosphere, near 400 parts per million. That's like only 20 people in all of the seats of an average sports stadium. Yet, this small concentration is enough to have a noticeable effect on our climate and weather. These trace molecules that absorb infrared light are called greenhouse gases, and the effect they have on the temperature of Earth's surface and the atmosphere is called the greenhouse effect. The concentrations of greenhouse gases change through time and are important for changing the temperature and climate of our planet. How do scientists know that these concentrations change through time? They either need to measure them directly, over and over, by filling a canister with a sample of today's atmosphere, or they need to find natural archives that have trapped samples of old atmosphere. Let's return to Thwaites Ridge. From those canisters of air, scientists have found that the concentration of CO2 molecules in the atmosphere has been increasing since they started collecting data 50 years ago. Thwaites Ridge is not unique. Scientists around the world have independently measured the same trend of increasing CO2. How will this trend influence the Earth's climate? We have seen that greenhouse gases, and CO2 in particular, play an important role in affecting the temperature of the Earth. Scientists have been investigating the effects of a changing CO2 concentration. This research has been happening for decades at places like Thwaites Ridge, but a handful of decades is not very long if we're trying to get a bigger picture. Looking further back in time, before we began collecting and measuring air directly may seem like a challenge, but researchers have found some clever solutions. In Antarctica and Greenland, natural archives of air can be found in bubbles trapped in the thick ice caps. Year after year of falling snow compacts into ice, trapping air in the process. Scientists sample the trapped air by drilling ice cores as deep as 2 miles over 3 kilometers down. They go 10 meters at a time, like pushing a giant straw through a layer of cake. The further down that scientists drill into the ice, the further in the past they can observe the CO2 levels. The air bubbles in the ice provide a record of Earth's ancient atmosphere, allowing us to measure the history of CO2 concentrations over hundreds of thousands of years. Our measurements of the amount of CO2 over time shows that it goes through cycles. The amount of CO2 bounces between lower concentrations in ice ages and higher concentrations during warm periods, or what we call interglacial periods. CO2 has been doing this for at least 800,000 years, as far back as we have ice sample data. What causes these large natural cycles, and what makes them so regular and timed? We find an unexpected answer in research from the early 20th century. An astrophysicist named Milutin Milankovitch was investigating how the Earth's movements change over time. Changes in Earth's tilt, wobble, and the shape of its orbit control how much sunlight is received at different points in the year, and how that sunlight is distributed across the globe. For example, the summer months of June and July in the northern hemisphere occur when Earth's axis is tilted towards the sun, coinciding with when the Earth is actually farthest from the sun. The reason Earth has seasons at all is because its axis is tilted. The Earth is currently tilted 23.4 degrees relative to its path around the sun. But over 41,000 years, this tilt varies between 22.1 and 24.5 degrees. The Earth is currently becoming less tilted, meaning that summers and winters should gradually be getting less extreme. But this isn't the only natural variation the Earth goes through. Over a period of about 26,000 years, the Earth itself wobbles like a top. This is called axial precession, and it means that the North Star will no longer be Polaris in a few thousand years. This wobble will shift the timing of the seasons. The Northern Hemisphere's summer will happen in December, about 13,000 years from now. If we fly out, we could see that the Earth's orbit precesses over 112,000 years, shifting the time of the year that the Earth is farthest from the Sun. This also affects the timing of the seasons. Even the shape of the Earth's orbit changes, oscillating between more circular and more oval, spanning 100,000 years. Our orbit fluctuates from 99 to 96% circular. Rooted in the interactions between the planets, gravitational pulls from the Sun, Jupiter, Saturn, and the Moon drive all the oscillations. Together, these slow changes combine to give Earth a complex dance of how strong the seasons are and in what time of the year they happen. This dance has major effects on Earth's climate and ice age cycles. Altogether, this means that the intensity of sunlight reaching the Earth varies in a predictable way over time due to variations in our orbit. Natural changes in sunlight interact with Earth systems that influence CO2 levels, such as volcanoes, biological activity, and the oceans. This drives a cyclical greenhouse effect that changes Earth's global temperature. The air samples trapped in bubbles from ice cores have shown that the amount of CO2 in the atmosphere has bounced between 180 and 280 parts per million over the past 800,000 years. This 100 parts per million variation, or 1/100th of 1% change, may seem small, but it contributes to the large variation in Earth's climate. The difference in average global temperatures between an ice age and an interglacial period is only 11 degrees Fahrenheit, or 6 degrees Celsius. Now, the natural pattern has been disrupted. Present CO2 concentrations have rapidly risen to exceed 400 parts per million. Fossil fuels like coal, oil, and natural gas form over tens of millions of years from buried ancient organisms. When extracted and burned for energy, fossil fuels release huge amounts of carbon dioxide and other greenhouse gases. Humans in modern industrial civilization have figured out how to extract and use fossil fuels at an incredible pace. Worldwide, we consume over 4 billion gallons, that's 15 trillion liters, of oil per day. It took the Earth tens of millions of years to generate this resource, and only a fleeting moment to undo it. Up until now, the Earth has undergone regular patterns of global temperature changes due to natural sunlight and CO2 fluctuations. Today, we are drastically shifting the balance by adding vast amounts of CO2. How will this affect the Earth, and how could we figure out what to expect? The world of science relies on a process called peer review, where scientists share their research and other scientists try to find mistakes in their work. In doing so, the science community develops a more accurate picture of our home planet. Analyzing the history of Earth's climate, today's observations, and the laws of physics, it's possible to make more accurate predictions about our future. You can think of this as an everyday example. If you reach into a freezer and grab an ice cube and set it out on a plate, how long will it take to melt? To answer this accurately, we would need to know how cold is the ice cube, how warm is the room, and how big is the ice cube. Depending on our answers to these questions, we can use physics to model and therefore reliably predict how fast the ice cube will melt. Now imagine repeating this experiment millions of times. Your predictions of the melting ice cube would become much more accurate. Icebergs and glaciers are Earth's giant ice cubes. How long will it take them to melt? Scientists around the world are collectively taking millions of measurements of our environment to model how it will change over time. However, modeling the interconnected climate system can get very complex. Scientists use powerful supercomputers to do billions of calculations. The amount and types of data used, the detail of the model, and the laws of physics incorporated all lead to slightly varied predictions from different teams of scientists. Despite the variability in the models, however, they all point to the same general prediction. Our Earth is warming, and will continue to do so until we can decrease CO2 levels. How will we prepare to face a changing Earth? Some models show that if we curb our emissions, the worst consequences such as sea level rise, ocean acidification, severe weather, drought, and population displacement can be reduced. We can each make decisions on a personal, local, and commercial level that add up to a global difference. We can have an impact by reducing our dependence on fossil fuels, thereby emitting less CO2 into the atmosphere. Renewable energy production is a common strategy for reducing carbon emissions. Solar panels and wind turbines can be placed in many different locations, including parking garages, road signs, and the roofs of schools, businesses, or your own home. Architectural design choices can also have a big impact on energy consumption. Some of the most advanced passive cooling technologies were developed from ancient Arabic and Persian architecture. These clever designs use carefully positioned vents to maximize airflow and minimize heating from sunlight. Modern architecture can make use of these same principles, minimizing energy used for heating and cooling. You may have heard of LEED certification, which recognizes buildings that use less energy, save money, and provide sustainable solutions. We can all make daily choices that collectively reduce our energy consumption, benefiting our families and communities. Walking, biking, carpooling, or using public transportation more frequently reduces your CO2 production and air pollution. LED light bulbs in our houses are much more energy efficient. Purchasing local food supports our community farmers and reduces fossil fuel consumption from importing food. People from all areas and occupations have been extremely creative and thoughtful about developing strategies to respond to climate change and move us away from the warmer Earth that models are predicting. From the remote mountain shack of Niwot Ridge, through ancient bubbles in Antarctic ice, and into our own homes, we have explored how and why our climate is changing. Human carbon emissions are warming our planet, and will continue to do so until we do something about it. Millions of dedicated citizens are taking action. Tens of thousands of researchers have devoted their careers to climate science. Engineers are building sustainable technologies, while forward-thinking leaders and entrepreneurs are enacting strategies for the future. Countless people like you and me are witnessing climate change in our own backyards and making small adjustments in our lives to reduce our carbon emissions. We can all make a difference. The most important thing we can do is keep talking about climate change with our families, friends, and leaders. We all share the future.